In this episode, we take on one of the most practical and misunderstood questions in modern governance. Before an organization deploys an artificial intelligence (AI) system, how should it compare different model types and decide which one actually fits the job? Many beginners hear the term AI and picture one broad category of smart technology, but that picture is too simple to guide a real deployment decision. Different model types solve different kinds of problems, require different amounts of data, create different risks, and place different demands on the people who must supervise them after release. That means choosing a model type is not just a technical preference or a purchasing decision. It is a governance choice, because the type of model you select will shape accuracy, explainability, cost, operational burden, user trust, and the kinds of harm that may appear if the system is used poorly or placed into the wrong workflow. A responsible organization therefore compares model types before deployment rather than starting with whatever looks most impressive in a demonstration. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful starting point is to stop thinking about models as products and start thinking about them as tools built for different kinds of work. A hammer, a thermometer, and a map may all be useful, but nobody chooses between them by asking which one is the most advanced in the abstract. The right choice depends on the task. The same is true with AI model types. Before an organization asks whether it wants a language model, a vision model, a recommendation model, or a simpler predictive system, it should first ask what exact problem needs to be solved, what kind of output is needed, and how much freedom the system should have when producing that output. If the goal is narrow and structured, a broad and highly flexible model may create unnecessary risk. If the goal is open-ended and language-heavy, a smaller scoring model may not be the right fit. Beginners should learn early that model choice starts with the job, not with the hype surrounding a technology category, because the wrong match between problem and model can create trouble even before the system reaches production. One of the most common model families organizations consider is the predictive model, which is often part of what people call machine learning, ML. A predictive model usually takes in known features and produces a bounded output such as a category, a score, or a numerical estimate. It may answer questions like whether a message looks like spam, how likely a transaction is to be fraudulent, or how strongly a case should be prioritized for review. These models are often useful when the organization has a clearly defined target and wants consistency around a repeated pattern rather than creative output. For a beginner, the most important feature of a predictive model is that it usually operates inside a narrower decision space than a generative model. That narrowness can be a strength. If the task is well defined and the possible outputs are reasonably constrained, a predictive model may be easier to evaluate, easier to monitor, and easier to defend than a system designed to generate long, flexible, human-like responses. Within that broad predictive family, different subtypes serve different purposes. A classification model helps place something into a category, such as safe or unsafe, likely or unlikely, approved or escalate for review. A regression or scoring model estimates a number, such as a risk score, demand forecast, or expected wait time. A ranking model helps order choices, which can be useful in recommendation, search, prioritization, and triage settings. These differences matter because they shape the consequences of failure. If a classification system mislabels a small percentage of cases, the harm may be manageable in one environment and severe in another. If a ranking model places the wrong items near the top, users may overfocus on weak priorities while missing something more important lower down. For beginners, the lesson is that even inside one model family, the organization still needs to ask what form of judgment is being automated. Is the model assigning a bucket, estimating a value, or ordering options? That distinction affects both the usefulness of the system and the risks surrounding its deployment. Generative models represent a very different type of system, because instead of selecting from a fixed set of labels or estimating a score, they create new content such as text, images, audio, code, or summaries. That makes them feel more flexible and often more exciting, especially in public conversation. A generative system can draft responses, rewrite documents, answer natural language questions, describe images, and support many other tasks that do not fit neatly into a narrow output structure. Yet that flexibility comes with trade-offs. A system that can produce many kinds of outputs is also a system that may produce plausible but inaccurate material, overconfident explanations, unwanted bias, or content that drifts beyond the intended scope of the workflow. For a beginner, the key point is not that generative models are bad or unsafe by nature. It is that they solve a different class of problems. They are most useful when the organization truly needs open-ended generation or interpretation, and less useful when the work requires tightly bounded, highly repeatable judgments that could be handled more safely by a simpler model type. Another important comparison is between model types defined by the kind of input they handle. Some models work mainly with text, some with images, some with speech, and some with multiple types of information at once. A system focused on natural language processing, NLP, may be a strong fit for contracts, emails, policies, support tickets, search queries, and other language-heavy environments. A system designed for computer vision, CV, may be much better for photographs, medical images, manufacturing inspection, or physical scene analysis. Speech models may fit call transcription, voice commands, or audio summarization. Multimodal systems are broader still because they can combine text, images, and other signals. For beginners, this comparison matters because organizations sometimes choose a model that sounds advanced without asking whether it matches the information actually flowing through the workflow. If the deployment depends mainly on documents and written instructions, a text-oriented system may be appropriate. If the deployment depends on visual evidence, then a language-only system may create awkward and unreliable workarounds rather than real capability. A related comparison involves the difference between task-specific models and broad foundation models. A task-specific model is built or configured for a narrower purpose and often works best when the organization knows exactly what it wants the system to do. A foundation model is trained more broadly and can be adapted to many tasks, often through prompting, fine-tuning, or surrounding workflows. One well-known kind of foundation model is the large language model, LLM, which can support many language-based tasks from summarization to drafting to question answering. For a beginner, the important difference is that a task-specific model may offer tighter focus, clearer evaluation, lower cost, and easier governance for a narrow use case, while a foundation model may offer flexibility across many use cases but can introduce greater complexity, broader uncertainty, and more operational control needs. Organizations should be careful not to treat flexibility as an automatic advantage. Sometimes the best deployment choice is the model type that does one modest job well, not the one that appears capable of doing everything at once. Organizations also need to compare model types based on how they learn from data and what that implies for readiness. Some models depend heavily on labeled examples, which means humans must have already defined what correct outcomes look like for past cases. These systems can be powerful when the organization has strong historical records and a clearly measurable target. Other models are better at finding patterns, grouping similar cases, spotting anomalies, or supporting broad language tasks without the same kind of tightly labeled history. That distinction matters because the availability and quality of data often determine whether one model type is realistic and another is not. Beginners should understand that no model type is magical enough to escape the data environment around it. A deployment choice that ignores the organization's actual data maturity is often a poor choice, no matter how capable the technology seems in public examples. Comparing model types, therefore, means asking not only what the model can do in theory, but what kind of evidence, labeling effort, and data discipline the organization can actually provide to support it responsibly. Explainability is another major factor when comparing models, especially in sensitive contexts. Some model types are easier to interpret than others, either because their logic is simpler, their outputs are narrower, or their behavior is easier to trace against input features and known patterns. Other models, especially highly flexible generative systems or complex deep learning systems, may be harder for ordinary operators to explain even when they are useful. That does not automatically make them unsuitable, but it changes the governance burden. If a system influences decisions that affect access, safety, fairness, or legal rights, the organization may need a stronger case for why a less interpretable model is still justified and what compensating controls will surround it. For a beginner, the key lesson is that the most powerful model is not always the most appropriate one. In some settings, a model that is a little less capable but much easier to explain, monitor, and challenge may be the wiser deployment choice because it better fits the seriousness of the decision environment. Operational burden is another area where model types differ significantly. Some models are lightweight enough to run quickly, cheaply, and with modest infrastructure requirements. Others need significant computing power, more expensive hosting, more careful scaling, or more complex monitoring after release. A generative model with broad language capability may create higher inference costs, longer response times, and greater uncertainty around output variation than a narrow classification system. A computer vision deployment may require different hardware, storage, and privacy controls than a text-only system. For a beginner, these operational differences are part of governance because they affect what the organization can reliably support over time. If a system is too expensive to monitor properly, too slow for the workflow it enters, or too complex for the available technical team to maintain, then the deployment may be weaker than the business case first suggested. Comparing model types responsibly means asking what it will take to run the system day after day, not just whether the model performs well in a controlled demonstration. Maintenance and update burden should also shape the comparison. Some model types remain relatively stable if the environment is predictable and the task is narrow. Others may require more frequent retraining, more frequent adjustment of prompts or surrounding logic, more active tuning of filters and guardrails, or more careful review when upstream conditions change. A broad generative model integrated into a dynamic workflow may need constant attention to instructions, retrieval content, safety settings, and post-release testing. A narrower predictive system may still need monitoring for drift, but the paths of change may be easier to define and measure. For a beginner, this comparison matters because many organizations focus heavily on initial deployment and underestimate what different model types demand afterward. A model that looks easier to deploy because it seems flexible may later prove harder to govern because it changes behavior across contexts in ways that are less predictable. Strong model selection, therefore, includes asking what kind of long-term stewardship the organization is genuinely ready to provide once the system is live. Risk profile is another major point of comparison. Different model types fail differently, and those failure patterns should influence deployment choice. A predictive model may misclassify or misrank cases. A recommendation model may amplify weak signals or create feedback loops. A generative model may fabricate details, produce unsafe content, or sound persuasive when it is wrong. A vision model may struggle with image quality, angle, lighting, or representation gaps. A multimodal system may inherit several categories of weakness at once. For beginners, the important lesson is that a deployment decision should never focus only on average performance. It should also consider the shape of failure. What kinds of mistakes does this model type tend to make? How noticeable are those mistakes to human users? And how costly would they be in this specific organizational context? A model type that fails quietly and persuasively may require stronger safeguards than one whose errors are more visible and easier for trained staff to catch. Human oversight interacts with model type in important ways as well. Some systems are easier for a human reviewer to supervise because the outputs are short, bounded, and tied to a known decision path. Other systems create long, polished, or open-ended outputs that can subtly encourage overtrust, especially when users are busy or under pressure. If a model type produces material that looks thoughtful and complete, staff may be more likely to assume it is correct, even when the system is drifting outside the limits of its competence. For a beginner, this is one of the clearest reasons model comparison belongs inside governance rather than being left only to technical teams. The organization must ask whether the chosen model type fits the actual human oversight environment. Do the people around it have enough time, training, and authority to catch its characteristic errors? Or will the model's style and complexity make meaningful review less realistic in day-to-day operations? The answer can change which model type is safest and most defensible to deploy. There is also a strong temptation for organizations to begin with the most fashionable model type and then search for a use case that fits it. That approach usually creates unnecessary friction. A wiser method is to compare options against the actual deployment goal, the stakes of the decision, the input type, the data environment, the workforce, the need for explainability, and the operational reality after release. In some cases, the right answer may be a simple predictive model. In other cases, it may be a broader language model placed inside a tightly governed workflow. In still other cases, the best answer may be that no current model type is mature enough or proportionate enough for the use case being proposed. Beginners should understand that responsible selection includes the option not to deploy, to narrow the scope, or to start with a more modest model type first. Comparing model types is therefore not a contest to crown the most advanced technology. It is a disciplined exercise in choosing the model whose strengths, limits, and governance burden best match the organization's actual needs. A practical way to pull all of this together is to imagine an organization deciding how to improve its internal support process. If the goal is simply to route tickets into the right queue, a classification model may be enough. If the goal is to prioritize which cases need faster review, a scoring or ranking model may be more appropriate. If the goal is to help staff draft responses to varied questions, a generative language model may have real value. If the process depends on reading screenshots or uploaded images, then a vision or multimodal model may deserve consideration. Each option brings a different balance of flexibility, explainability, cost, and governance complexity. For a beginner, the lesson is not to memorize every model family. It is to learn how to ask the right comparison questions. What kind of output is needed? How bounded should it be? What data supports it? How visible are its likely errors? And what kind of oversight can the organization truly provide once the system is deployed in real workflows rather than ideal test conditions? As we close, the central lesson is that model choice is one of the first major governance decisions an organization makes before deployment. Different AI model types are built for different jobs, depend on different forms of data, create different operational burdens, and fail in different ways. Predictive, ranking, generative, vision, language, multimodal, task-specific, and foundation-based systems all offer value in the right setting, but none of them is automatically the best choice in every environment. For a new learner, the most important habit to build is proportional thinking. Start with the real problem. Compare the model types that could solve it, and judge them not only by capability, but by explainability, oversight needs, cost, risk pattern, maintenance burden, and fitness for the organization's actual data and workforce. A responsible organization does not ask which model type sounds smartest. It asks which one can do the needed work in a way that remains understandable, manageable, and defensible once the system leaves the lab and enters the real world.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.